Hello everyone, so in this lecture we will study about Ampere Circuital law, solenoid and toroid. So let's start from Ampere Circuital law. First of all, the Ampere Circuital law and Biot-Savart law both determines the magnetic field. Ampere Circuital law says the magnetic field, the line integral of the magnetic field around a curved closed curve is equal to mu naught times of the total current which is flowing inside the curve. Suppose there are wires, suppose this wire in which current is flowing inside the paper I1, the another wire current is flowing outside the paper I2, the another wire I3, and suppose there is one more wire in which current is I4. Now if we take a closed loop like this, then the line integral around this closed curve, first of all in Ampere Circuital law we take closed curve and the line integral for this will be b dot dl. dl is the line element, that means we take a element around this closed curve and the length of this element is dl. Suppose it is in this direction, then b dot dl will be written like this: mu naught minus I1 minus plus I2 minus I3, right? So if we curl our fingers in direction of dl, then the thumb will represent the positive direction of the current. So here if we curl our fingers in this direction, the thumb will represent in this direction. So current which are flowing in this direction will be written here positive and opposite currents will be written as a negative. So if the b dot dl is 0, that means net current is 0, and this net current includes only the inside currents. Here I4 will not be included because I4 is the outside this curve, and this does not mean that B is 0. B can be 0 over B cannot be 0, right? So if integration of b dot dl is 0, that does not mean that magnetic field is 0, right? Now this Ampere Circuital law is first of all valid for closed curve, and the second I net is the total current with sign inside the loop, right? And this integral does not depend shape of this curve and position of wires. So this b dot dl, these wires, if these wires are not in this pattern, suppose these wires are closely, then the b dot dl will be the same because we are putting only the currents. It does not depend on the position of the wires and does not depend on the shape of the curve. Now we will solve a question depending on this law. Question is, find the value of b dot dl for the loop L1, L2, L3 in the figure shown. The sense of dl is mentioned in the figure. So sense of dl is already mentioned in this figure. Here it is mentioned in this direction. So if we curl our fingers in this direction, then thumb will represent in this direction, that means current which are flowing in this direction will taken be with positive sign. So for loop L1, B dot dl will be mu naught. In L1 current I1 and I2 are flowing. I1 is in upwards direction, though I1 will be with positive sign and I2 will be with negative sign. Similarly you can write for loop L2, this will be B dot dl and this will be mu naught. For loop L2 there are three currents in this loop. So first current here I4 in upward direction, so I4 will be with positive sign, then I1 also in upward direction and I2 in downward direction. Similarly you can write for L3, it will be 0 because there is no current. So if integration of B dot dl is 0, that means the net current is 0. But we cannot say about the magnetic field. Now we will study about solenoid. So solenoid is a cylindrical coil actually, in which the turns are closely and tightly wound around its cylindrical shape, and these wires are insulated wire, and if current is flowing in this direction suppose, then it will come out the solenoid like this. And suppose the length of this solenoid is L, number of turns are N and the radius is R. Now if we draw the solenoid like this, so at this point current is coming outside the paper at this point, and at this point current is going inside the paper, so we can draw the solenoid like this, right? So now you can check if we curl our fingers in the direction of the current. So direction of the current is like this, so thumb will represent the direction of magnetic field. So for one loop if you see, the magnetic field direction will be like this, so for every loop direction of magnetic field will be like this. So magnetic field lines will be like this inside this solenoid, and outside the magnetic field will be 0. So now if we write the formula for magnetic field, mu naught Ni by 2 cos theta 1 minus cos theta 1. This is valid for finite length solenoid, and here first of all here N is the number of turns per unit length, so this will be capital N by length of the solenoid. So suppose this is the solenoid and we are calculating the magnetic field on the axis of this solenoid. Inside the solenoid, suppose here is a P point, so the P point makes an angle with one end and axis of the solenoid, that is theta 1, and with other axis it makes another angle theta 2. Remember these angles are measured in same direction, right? So this will be the formula for finite length solenoid. Now if we talk about infinite length, infinite length solenoid, or we can say ideal solenoid. So in this case the length of the solenoid will be very large in comparison to the radius of the solenoid. So for this, if we are calculating B inside the solution, then it will be mu naught Ni, and at one end it will be mu naught Ni by 2. How we have calculated this? From this formula, at one end, if we are calculating at one end, suppose we are calculating at this end, so for this end angle will be with axis pi by 2, so theta 1 is pi by 2. Now for other end is at infinity, that means with other end the angle will be pi by 2. pi. So theta 1 will be pi by 2 and theta 2 will be pi. So if we put in this pi by 2 minus cos pi will be minus 1. So this will be mu naught Ni by 2. So this will be the B at the end of the solenoid. Now for inside point, suppose here is a inside point. So angle these points make with this, and it will be around 0 because it is a infinite length solenoid, and with this end angle will be near to pi by 2, pi. So cos 0 is 1, cos 0 minus cos pi, it will be 2. So it will be mu naught Ni. Now if we draw the curve for both solenoid, real solenoid and for ideal. Real means finite length and ideal means infinite length. That means L is very large in comparison to radius. For real solenoid, magnetic field will be like this, and for ideal solenoid, magnetic field inside the solenoid will be constant and value of this will be mu naught Ni. At the end of the solenoid it will be mu naught Ni by 2. Now we will talk about toroid, and before that we will solve a question. So in this question we are given a solenoid of length 0.4 meter. That means length is given 0.4 meter, diameter is given 0.6, radius होगी 0.3 meter, consists of a single layer of 1000 turns of fine wire carrying a current. So number of turns will be 1000, current will be 5 into 10 raised to power minus 3 ampere. Find the magnetic field on the axis at the middle and at the end of the solenoid. So for middle of the solenoid we have to calculate, actually formula is mu naught Ni by 2 cos theta 1 minus cos theta 1. Now you have value of n is the capital N of the upon length. So n is given, length is 0.4 meters, so you can calculate n. Now we have to actually calculate theta 1 and theta 2. So suppose this is the solenoid and we have to calculate here in middle of the solenoid. So if the length of is given 0.4 meter, then P, this is the center, suppose this is C1. So PC1 will be L by 2, that means 0.2 meter. This is C1 and suppose this is a point Q. So C1Q will be radius, that is 0.3 meter, and this will be PQ. You can calculate from Pythagoras theorem. It will be square of PC1 square plus C1Q square, right? So if you have all three sides of a triangle, then you can calculate the cos theta 1 easily. Cos theta 1, this angle is theta 1, cos theta 1 will be PC1 upon PQ. Now we have to calculate cos theta 2. So this angle is theta 2. Suppose this angle is alpha. Suppose this angle is alpha. And this is center C2 and this is suppose S. So first of all, cos of alpha will be PC1 PC2. PC2 is nothing but the L by 2, 0.2. upon PS. C2S is the radius and PC2 is the 0.2. So cos alpha will be, actually PC1 is 0.2 and this PS will be equal to PQ. Right? So cos alpha will be this. That means cos theta 1 and cos alpha both are equal. Now cos of theta 2, we can write theta 2 angle like this, cos of pi minus alpha. Can we write like this? Yes. And pi minus alpha, cos of pi minus alpha is minus cos alpha. Cos alpha value we know from here. So now you have cos theta 1, cos theta 2. So you can calculate the value of magnetic field at the middle of the axis. Now for end point, suppose this is the solenoid and we have to calculate here. So for here, this angle will be theta 1 and this angle will be pi by 2. Now we have to calculate this angle. And this angle is theta 2. So suppose again this angle is alpha, right? And suppose this is C1, this is P and this point is C2. Now C1, C2 is length of the solenoid, PC2 is radius. So PC1 will be square root of C1 C2 square plus P C2 square. So cos of alpha will be P C1 C2 upon P C1. And cos of theta 2 can be written like this, cos of pi minus alpha. So this will be equal to minus cos alpha. So now cos theta 2 is minus cos alpha, that means this value, and cos theta 1 will be here 0. So you can put the values of cos theta 1 and cos theta 2. You will find the magnetic field at the end of the solenoid. Now we will study about toroid. So in toroid, the solenoid, if we join the both end of the solenoid, we will find the toroid. So toroid is actually in this shape and the wire is similarly insulated wire will be tightly and closely bound around this shape, right? So suppose the inner radius of this core is R1 and outer radius is R2 and magnetic field will be mu naught Ni. N will be number of turns per unit length. Now if we suppose this current is going in this direction, right? So at this end current is going inside the paper and at this end current is coming outside the paper. So we can draw this toroid like this. Now inside this toroid, here a magnetic field will be 0 and outside this toroid magnetic field will be 0. So magnetic field will be here only inside R1 R2. So here the magnetic field will be mu naught Ni and N will be number of turns per unit length and this will be number of turns upon 2 pi Rm. This Rm is the average radius. This will be R1 plus R2 by 2. So remember this formula and this one also, this one also. Now we will solve a question based on this formula. In this question we are given a toroidal coil has 2400 turns and carries current 250 milliampere of the current, producing a magnetic field. This the parameter of the toroidal coil is. So first of all, B is mu naught Ni. If we put the values, B is given 31.5 into 10 raised to power minus 4, mu naught, you know, 4 pi into 10 raised to power minus 7. Remember this value of mu naught. Then n is number of turns. Number of turns here given 2400 upon 2 pi rm. 2 pi rm is the actually parameter of the toroidal. ये average parameter होगी, and I is given 250 milliampere. So if we denote this term as P, because हमें parameter ही find करना है, so parameter will be 4 pi into 10 raised to power minus 7 into 2400 into 250 into 10 raised to power minus 3 upon 31.4 into 10 raised to power minus 4. This is very simple calculation because pi value is 3.14. So this and this will be cancelled out, and here it will remain 10, right? Now this and this, multiply this and this first, then this will become 1000 and 10 raised to power minus 7 into 2400 into 10 raised to power minus 3 and upon 10 raised to power minus 3, right? So this is now very simple calculation. You have to calculate only 10 raised to power. So now in next lecture we will study about force on a moving charged particle and force on current carrying conductor in a magnetic field. And this question was asked in last recruitment in shift 1. तो इस लेक्चर को यहीं पे एंड करते हैं.